Everyone, welcome. This one's going to be a little bit of an interesting presentation because we have to share a mic, but I think that we'll do fine. So my name is Carey Payette, and I'm a senior software engineer for Follas Software, as well as a senior IoT architect for the Mewat Corporation. So today we're going to be talking to you a little bit about an IoT device that we're producing and getting to market with it. So this is going to be a presentation that will tell you some of the things that you need to know if you are looking to go and sell your devices to the world.
And my name is Jason Follas. I'm also with Falafel Software, also with Mewat Corporation. So this is the talk that we wish that we had seen 6 months ago, because there's a lot of learning. Some of it was expensive lessons learned. So hopefully this helps you out if you're looking to take an IoT device to market.
All right, so we're going to start with before inception. All right, so why is IoT important? For one thing, IoT, well, first, if you need a definition, I'm sure IoT is kind of one of those buzzword bingo things that is quite popular right now. But IoT is essentially the technology of connected devices. So really, if you have devices that are talking to each other, you're doing, again, kind of loosely with the term IoT. So why it's important is because in 2015, Gartner estimated that there's 4.9 billion connected devices out there right now. And that means that there's $69.5 billion of services, and this has everything to do from software development as well as hosting. So right now is definitely a prime time to get into it. 2016 is estimated to grow another 39% from those numbers. So this is something that is a freight train. It's not slowing down. It's going 1,000,000 miles per hour. So by 2020, the estimated number of connected devices will be $25 billion with an estimated spending of $263 billion. So, and this is encompassing everything. I'm talking about the hobby, consumer, and enterprise sectors. So I'd like to stress that a little bit. That would be billion with a B. So in response to that, my boss, Lino Tadros, actually attended my CodeMash presentation. And in there, I was doing an introductory talk on IoT, where it was more of a technical talk, but I did introduce IoT and some of the statistics that I just rattled off to you. So that really firmed up in his mind that IoT was a place that we wanted to position ourselves in. So at Falafel Software, he decided to choose a group of us, and we formed the IoT team at Falafel Software. So on top of creating this team, it's also important to know that we also have external companies coming in asking for IoT solutions, how to develop their product, and are handing those off to us to implement. So we really wanted to make sure that we hit the ground running, that we were versed in everything that we needed to know in IoT. So as soon as the IoT team was established, we went ahead and started exploring ecosystems. So we decided to look at things like the Raspberry Pi, the NetDuino, the Arduino, the Espressif, which is the ESP8266, as well as the particle cloud and particle devices. We also needed to get information off the devices themselves. So we decided to do deep dives into the communication protocols. So some of the ones that we were looking at are like Bluetooth, BTLE, Wi-Fi, as well as Zigbee. And of course, that data needs to go somewhere. We need to consume it somehow. So putting the I in IoT, we also did deep dives into various cloud services. Among those were the Amazon Web Services, the Particle Cloud, and Microsoft Azure. Oh, that was magic.
So for Mewat's what we're talking about today. That's the product that started out as an IoT project. something that was just existed, or something that existed just on our desks, and we brought it, or we're bringing it to market. So that's the whole point of this talk, is our journey along that way. So that journey started with our boss. He had a problem. He bought a vacation home in Hawaii, and that wasn't the problem, by the way. But after spending a couple weeks there and coming back, and then and he lives in California, by the way, he received his first electric bill for just being there for 2 weeks. And it was almost as much as him living at home full-time in California. And he was like, well, Hawaii's got the most expensive electric rates. That makes sense. But I have no idea where my electricity is being wasted. He had no idea. He suspected it was his pool. Was it his pool pump? Who knows? How do you even measure that? So that was the genesis of Mewatt. Mewatt's a device to allow you to measure the energy consumption of some point of use. Some outlet is our first version. And we're not only interested in measuring that, we want to get the data up there so that we can do things in the cloud like establish trends, figure out if you just turn off your power for between these two times of the day, you could save $15 a year. Those types of analysis is really where we wanted to go with the software, but we also needed the hardware to take us there. Well, this has both of our pictures on it, so we can both talk. So from the hardware side is kind of commodity, right? We're not the first ones to measure how much electricity a device is using. There's the kilowatt, there's the Wemo, there's something which is now bankrupt, the Quirky device, that was partnership with GE, and many more. So one interesting thing that we noticed was that most of these devices that you can buy off of Amazon and Home Depot and Lowe's, they were running about $40 to $50 a piece. And the exception was the kilowatt. The kilowatt's about $20 a piece. The downside of the kilowatt, though, is that you have to walk over to the device to see how much it's using, and you're not getting the trending type of information. So like I said, the software was very important to us. We wanted to focus on the software as our value add, but none of the hardware that we examined, and we looked at a handful of them, so we didn't exhaustively go through all the hardware. But none of the hardware that we examined gave us like an API to allow us to consume the data as we wanted to. So that's why we decided to build our own device.
So the next step is definitely creating the hardware. So we had a problem to solve. We needed to measure the electricity, and we needed to find out how to do that. So here we are, a couple software devs that we were tinkering in a little bit of the IoT space, but hadn't done anything more than hobbyist type projects. So the way that we started was to read data sheets, more data sheets. So that pile is actually quite a lot larger. But one of the things that it did do for us, though, is finding the number of sensors that are out there that perform electrical readings. It really opened it up and motivated us to give these things a try and find out which ones were the best of breed.
So our biggest problem was that we needed to measure the current that was coming out of the wall flowing through your device, because that's how we are able to calculate wattage then, in watts or kilowatt hours is how you are billed monthly for your bill. So in order to equate the point of use to dollars, we had to be able to measure that current. So that was the focus of the types of devices that we were studying data sheets for. We found a couple interesting ones. This one used a Hall effect sensor. So between the IP plus and the IP negative, there's just a short in there. So the electricity is flowing through, very low resistance, and there's a magnetic Hall effect sensor parked right against there. So it's able to as more current flows through, the magnetic effect shifts on that, and we're able to detect that. The output of this was 5 volts, so we got 0 to 5 volts representing some scale of current. And then we had another problem then, taking that 0 to 5 volts DC, and we had to read it into an ADC in order to do anything with it. One other problem that we came with, and by the way, we did prototype with this originally, and this was going to be our solution until we started realizing some of the deficiencies. One deficiency is that whole chain of reading the current through this and then having it output a voltage and then reading that voltage in through an ADC delayed our current reading from the voltage reading that we had. So the waveforms were slightly offset, and that caused an accuracy problem that we had to solve. We had to get the waveforms to be in sync in order to compare them, because when you're calculating like voltage amps, you want the highest volt and the highest current to be at the same part of the waveform. So we looked again, and we came across this one, and this is what's actually in our device. This is the Cirrus Logic CS5480. It's a two-channel, actually three-channel. It has a channel for voltage, and it has two current channels. And this is a really tiny device. It looks huge on this movie screen, but it's only 4 millimeters on one side. So hand soldering this was a little bit of a challenge in a prototyping type of scenario. What we learned, though, is that these inputs are just ADCs in themselves. They're differential ADCs. So the reference designs that we used when creating the circuit had a couple different options for the current sensing. The one that we went with was a shunt resistor. So you put a really low but fixed value in the current line. So all the current's passing through a 0.005 ohm resistor. And then the ADC is just measuring the voltage difference on one side versus the other side of that resistor. And then that equates to how much current's flowing through there because of Ohm's law. Because it's such a low resistance, there's hardly any heat being dissipated by this device. And it was also very low cost. So that's why we went with that in our device. Another option, by the way, if you're interested, is we could have used a current transformer. And this is basically just a transformer that goes around the line that's carrying the current, and we're able to get the reading out of that, because the current will induce a magnetic field in that, and that generates some kind of small voltage signal that we can then read by the chip. Now, the shunt resistor makes sense for the wall outlet design that we're plugging into the wall, because we have a fixed current, right? We have an outlet that we can actually plug something into and a fixed current. But Lena's pool pump scenario doesn't make sense to use a resistor like that. It makes more sense to use this, a current transformer. So our first device to market is going to evolve beyond that, because we have other scenarios that aren't supported by this first device. But we have a whole roadmap of other devices that are going to quickly follow.
All right, so our first goal when we were developing this product would be what your first goal would be, is developing that minimal viable product. So for us, in our case, we needed to be able to connect to the internet. We needed to measure electricity, as well as support remotely turning on and off the device through a relay. Oh, thank you. I'll do it for you. So this was our first proof of concept. So this was when we were still evaluating Raspberry Pi with Windows IoT Core. So you can see that we got to play around with breadboards, jumper wires, and we even got to split an extension cord in half. So that was a lot of fun. So yeah, definitely we were able to get good readings off of the device at this point. So that was why my boss looks very happy in this picture. The next step that we wanted to do was, obviously with the Raspberry Pi, the cost was going to be an issue, and also the footprint. So you're not going to stick a Raspberry Pi in a small wall outlet-sized device. So we decided that we were going to look at the Arduino, and Arduino has like a series of different Atmel chips that you can go down to pretty small. But we had discovered early on that I don't think it's dead. But anyway, with the Arduino, that we would have to have a separate Wi-Fi module. So again, we were seeing our footprint kind of get larger. So we decided to focus on modules that had both the processor as well as the Wi-Fi module all in one. So our next step was Photon. So Photon is a particle product, and it's Arduino compatible, so you can put your Arduino sketches in there and run them. They also have a full cloud service available, so I think it's $2 for the lifetime of the application up to a certain number of devices. So they would take care of things like the registration of the device. They would take care of things like over-the-air updates of software and firmware and so on. So while it did give us a reduced effort for software, the thing that came immediately clear to us that it resulted in a higher cost for the hardware itself. So that was one of our value propositions, is we wanted to come in under what the regular market values for these types of devices were.
So we kept looking at other platforms, other microcontrollers, basically other platforms to solve our problem. And the one that we landed on is one that I just happened to stumble upon when I was researching prices and capabilities and so on and so forth. And this is my new favorite device. This is the ESP8266. It's by a Chinese company, Espressif, and they're using a tin silica design, which from what I understand, it's kind of like a drag-drop way of making silicon devices. This company gives out the kit. If you need like GPIO or a real-time clock, something, you just drag that module over, drop it onto the silicon, and that becomes part of the plan. There's probably more magic to it than that, but that's, as I understand, why this chip was manufactured so cheaply. What's underneath this FCC tin here? We have the ESP8266 itself, which is a small microcontroller. It's again about 5 millimeters on one side. You also have a 4 megabit or a 4 megabyte flash memory chip that is wired to the ESP already, so you get storage out of the box. The ESP itself has Wi-Fi right on the silicon. So that's something that other platforms you need a separate, like a Broadcom Wi-Fi module in addition to your MCU. In this case, it's all one chip, so that means that they can sell the microcontroller for under $1 in volume. And this module that we see here that has everything that we needed all together as one unit, including a PCB antenna, sells for about $2.50 a unit. So it's very cheap, and it's very capable. The MCU itself is running at 80 megahertz, and it can be overclocked to 160. And the memory free, when our device boots, the memory that we have available to us is about 40K. So for about the memory footprint of a Commodore 64, you get 160 megahertz worth of processing. We also had to think about what user interface. So we're talking about a device that users are going to buy from Home Depot if everything works out well. And Carey's holding up the basic form factor there. So how do we get input, the bare minimum input and output to the user from the device itself before they're hooked up to Wi-Fi and whatnot? So we have to have things like a button. So the button can do things like turn the relay on and off when it's plugged in. But we also we opted to not have a separate button for reset. Instead, reset, we're just unplugging the device, plugging it back into the wall, and it handles the reset. If you hold the button as you plug it into the wall, well, that gesture says, I want to clear the Wi-Fi memory. And if you hold the button even longer and plug it into the wall, then you do a factory reset. So these types of things are the user interface that we had to bake into the hardware and also write the software to drive it. And also because they want to see that the device is alive, we have an LED that will flash different patterns based on what's happening at that time. For everything else, we're just going to defer to the web or to the phone app once the device is actually connected and broadcasting data up to the internet. So there is software that's running on the device, and software that's running on hardware is commonly called as firmware. And for this particular device, we're using an open source firmware. We're actually using a fork of the project. It's called Node MCU. Node is just the generic term for Node. It has no relationship to Node.js. But Node MCU exposes the underlying SDK, which is used to automate the hardware, up through a Lua language service. So we write scripts in Lua to automate the device, and then we're only dealing with scripts on a file system. So if we need to push an update, we're reducing the risk of breaking the device by dealing with files instead of rewriting the entire operating system, if you will.
So the next step on our journey, and what yours would be as well, is doing the schematic capture and the PCB layout. So there's a lot of CAD programs out there. They're fairly expensive and kind of hard to use, in my opinion. There's a lot of those out there, but what we stumbled upon was actually an online service, and the online service is called Upverter. And what's really nice about this is they have a freemium tier, so it's free for up to 2 private projects. So it's really, obviously cost effective. Another thing is that they crowdsource their part creation and footprint generation. So if you had your own CAD software that you have loaded on your desktop and you wanted to add, for instance, a resistor to your library, if it wasn't in that library's collection, then you would have to manually do it yourself by looking at the measurements in the data sheets. So what's nice about Upverter is they have a crowdsourced type library. So as parts are being created either by the concierge, which I'll talk about here in a minute, or if you manually create a part that wasn't in the library, they will verify it with the data sheet and then add it to the global library that's there. So essentially you're having crowdsourced part creation for your schematic and for your PCB layout. And what's also nice about this is full collaboration is also available. So, for instance, we had at least 3 of us working constantly on the PCB design and the schematic design. We were all able to go in there and see real time the changes that our coworkers were doing, and we could get on a Skype call and talk through things. So it definitely ended up being an excellent solution for us. And on top of it, Upverter also has export functionality, so you could also export your BOM as well as, that was bill of materials, and you could also export the Gerber files that you need to go to manufacturing. So finding parts, now this is a fun one. It's not as easy, oh, sorry, I was looking at the wrong slide. All right, so standing on the shoulders of others. So using the reference designs that are available inside the data sheets. They're there for a reason. They're there to get you up and running with the component, and they're also there to help you out when it comes time for certification. So you can prove to any certification authority that you are following the best practices and the recommended application for that component. So don't try to strike out on your own to do this on your own. Use what's there. Also take advantage of internet searches. So I know for our power supply, there was multiple reference designs out on the internet. So we just found the one that we thought suited our project the best, and we used that for our power supply.
So as we quickly found out, we're software people who just happen to play with hardware as a hobby, is how we started this. In software, if I want to download a component, it's instantly available. In hardware, if I want to try something out, I'm waiting a week for it to be shipped to my house because I don't have a Fry's or anything like that next door to me. So definitely not as easy as going to a Walmart and buying something. Some of the sources where we frequent is like DigiKey, Mouser. We get an idea for how much sourcing would be overseas by checking out Alibaba. And the other thing in the middle there is we found out that when you are talking to manufacturers or distributors about getting pricing, make sure you back that up in writing, because we've had, in our journey of going to manufacturing, we've had at least 1 or 2 prices that have changed on us, which dramatically impacted our ability to use that part. We had to evaluate whether to go to a different part, or we had to evaluate the final price of the build.
So yeah, definitely we can't stress that enough. Get your prices in writing. So after the parts have been procured, we were ready to start developing our first PCB. So a lot of the parts are small. Obviously, we're going into a small form factor. Some were hard to find, meaning that we'd have to go to the end of the internet to find some. I think it was our relay, the original relay that we had was almost impossible to find. Another thing to keep in mind too is some of these small resistors, they have minimum quantities of like 100,000. You have to order 100,000 of these resistors as a minimum quantity. Well, we only wanted 50 to start with. So you're taking that purchase, you're taking that cost ahead of time just so you can get the part that you desire. And also another thing that you need to keep in mind that like the surface mounting of these components is not an easy task. It requires specific tools, things like solder paste stencils, as well as a reflow oven and so on. But most importantly, the thing that you do need is really good eyesight. So this was, like, I don't know if you can see the detail of the finger lines of the fingerprint, but that is one of our components. So obviously, even when you're in that prototyping phase, do pay attention to the package size of the components that you're purchasing so you don't get stuck trying to solder something this size onto your board. And speaking of the PCB, when we started going through iterations of the PCB, we found that it was a better choice for us to go to a Chinese manufacturer. The shipping time is about 1 to 2 weeks. We did try domestic. It was probably about weeks different in the shipping time frame, but on the flip side, it was also 3 times the cost to have them developed domestically, and the quality of both were very similar.
So that's the electronics. We also have a physical part. We have a plastic enclosure that this has to fit into. So for prototyping, it makes sense just get a 3D printer and print it. One thing that we found out, though, and I'll say that none of us are mechanical engineers, so we had to outsource the whole mechanical engineering of this. And the guy we were working with is great. I mean, he's been in the business a while, and he thinks of things that we don't think of. So his artifact, he's working on off of a CAD program, and he just exports it and sends us STLs so that we can print it on our own printers. One thing about printing with a 3D printer like this, which lays down in layers, is that you have strength in certain directions and weaknesses in the other. So we have the button here on the side, and if we go to press the button in, that's flexing it against one of those layers. So the flaw with trying to test our device with 3D printing is that we kept breaking off the buttons. And really, until we go to like a full injection molding, we're not going to be able to solve that. So that's the downside of 3D printing. The upside is that any design changes can pretty much be tested and printed physically without requiring another outsourcing.
So also, again, on the 3D printing side, when you're going to manufacturing, you're going to be sending your PCBs out to be populated by a third-party company, obviously, because you're going to go to do volume. So one of the things that we also had to develop, and this one we don't need any injection molding for, is the test jig. So this is a way for when our PCBs are coming off the line that they're able to enter this into the test jig, run a program, and see if the PCB was assembled appropriately and passed our quality assurance. So this is also a 3D printed test jig that we created.
So now we have a device and we're able to collect electrical measurements. Now we need to get those measurements, all that data, up to the cloud. And the way that we're doing it is we're collecting a reading every 5 seconds. And that Cirrus Logic chip that I pointed out to at the beginning of the talk, that's programmable. So we can have it collect a reading every second, every 5 seconds, every 10 seconds, whatever we need to. We adopted 5 seconds because it seemed like a good compromise between frequency and accuracy. Also, to keep because we're shipping all of this data over our customers' Wi-Fi, and I don't know about you, but at least one of the cable providers in my city has bandwidth caps. So, with my kids watching YouTube and all that, it's quickly exhausted. And we didn't want to get in a situation where people were pointing fingers at us saying, the reason my kid can't watch Netflix this month is because of your device. So we intentionally kept the memory or the data footprint tiny, and we're broadcasting those every 5 seconds. So how do we get data to and from the cloud? We're using a protocol called MQTT. MQTT is a pub-sub model. It's a binary pub-sub that's over TCP. And also, there's WebSockets implementation of it too. So you can have a web page talking to an MQTT server, which is what Facebook Messenger uses, by the way. So on ours, we open up a TCP socket, and then our data, which is only maybe 100 bytes or less every 5 seconds, goes up over that binary channel, and there's really little overhead. Like with HTTP, every request that you send up that's not through WebSockets has a header, and we didn't want that header. And with MQTT, we're able to send up those 100 bytes without incurring the cost of the header. We would have considered something like WebSockets for the ESP, but it wasn't available in the firmware that we selected. So MQTT. Also, for some of the things we use, we do have our HTTP APIs, but that's mostly from our API talking to the portal where the user will be getting their data, or to the phone app.
Yeah, and we're also using MQTT for things like notifications in the portal. So you can get that's the WebSocket solution. So you can get that real-time signal R-like functionality using MQTT as well. So the next thing that we needed to look into is hosting. So cost is definitely a factor in this case. So basically, do your shopping. So depending on the size of what you estimate your network to be of devices out in the wild, you need to take that into account when you're shopping around for a cloud provider. For us, our solution ended up being Amazon AWS, so it was more cost-effective in our scenario. So it was more suitable for our selected technologies, and we also were able to take advantage of other services, including things like push notifications, EC2 virtual machines, and this is really the big place where we saved a lot of our money was on the virtual machines. S3 storage, Lambdas, which are basically little chunks of code that you can run ad hoc in the cloud. We're also taking advantage of code deploy, which will actually deploy our code based off of check-in that we have going through our Jenkins server. Will trigger a code deploy to our development environment so we can test it thoroughly. We're also using Redshift as our data warehouse for historical data.
So Mewatt's free to use. So if you as a consumer buy a Mewatt or buy up to 10 Mewatts as a residential consumer, we're not charging you for it. So because we're taking the hit on the software side up there, we're leaning heavily on open source software for building this. So for our MQTT, we're using, I'll say that we use a lot of Node.js in what we do. So for MQTT, we're using a Node.js app, I think is what you call programs that run on MQTT or on Node. And it's called Mosca. And one thing that we liked about Mosca is MQTT by itself doesn't define things like how do I prevent a user from subscribing to a topic that they don't have access to. It's not touchscreen. She's touching my, oh, now it's messing up.
Yeah, it went to Cortana.
Oh, did I say hello Cortana and it heard me? That was another talk. So Mosca allows us to do things like, based on this user, and they tried to subscribe to a wildcard topic, we're going to deny that action. So that was really attractive to us. We also use Redis and MongoDB. We write a lot of our own HTTP APIs, and we use Jenkins for the build server.
As for security, obviously with IoT, security is a huge deal, because if you get somebody that gets the keys to your castle, you can get in big trouble, especially if you have a lot of customer devices out there. So the approach that we took is using expiring JSON web tokens. And what JWT is It's a signed and an encoded token that contains application information as well as user information. And of course, it has a sliding, well, not a sliding, it has an absolute expiration, so these things refresh over time. We had decided to outsource our actual mobile app and web portal authentication, and the service that we're using for that is Auth0, which has the JWT backend. So we chose this because it had a large number of libraries available. So essentially, basically any technology that you can think of, Auth0 provides a library for it. And it's really easy to hit the ground running. So we have one for our web portal. We also have one for our Xamarin applications. So on top of that, we're using JWT as authentication between our internal services for authentication. So essentially, we don't have to use the Auth0 libraries. There's other libraries out there to decode tokens, but we adopted that model for authentication to our internal services as well. And then for any traffic that does go over the internet, we make sure that we have SSL implemented as well as secured web sockets. As for software licensing, and this is a little bit of a cost slide, with Apple it's $99 per Apple Dev. Android is a one-time fee of $30. We also have MSDN, where we're using Visual Studio, as well as Visual Studio Code, which is free. We're using Telerik UI for Xamarin to do some of the charting functionality in our Xamarin apps. We also subscribe, like I mentioned before, to the Auth0 services, as well as Raygun. And what Raygun does is you put that into your application, and it captures crash dumps as well as exceptions that happen in your application and informs you of it, even if your users don't. And on top of that, we're also free with MSDN. We're using Visual Studio Team Services. So that's where we have our source code. That's where we do our project planning and so on. So now we're going to talk about going to market, and this is the gist of our presentation today. So you're going to go big, take the plunge, go big, go home. This is the point of no return. So you have your device, and you're ready to go. It works. Everything's going good on the software front. So what's next? Certification. So we know that we have a device that's a consumer device. So if you look on the back of multiple devices, you could see like the UL certification, like just those letters that are kind of engraved on the back of devices. So we thought our product's done. We're ready for certification, or at least we thought we were ready for certification. So one of our lessons learned is definitely make sure that you get a certification authority involved early. This will save you a bunch of time, because when we're doing an iteration on our PCB board, you're looking at 3 weeks for each major change that you're going to do. So this is like changes of, parts that had footprint changes that caused the PCB to change. So definitely get them involved early. We'll just say that. So the certification testing that's required for your device is really specific to the device that you're trying to go to market with. So I can talk to some of the tests that are required on our side. We needed to separate our high voltage and low voltage areas. Any user interaction, so like from our button, for instance, we need to make sure that any abuse of that won't result in somebody electrocuting themselves. That's definitely a good thing. Believe it or not, there's sound requirements, and this is one that we just passed this week. The electronic components will actually generate noise, and they have to come in underneath a certain level. So flipping around capacitors and resistors and things like that will help with that. FCC, which was something luckily we didn't have to deal with because our ESP8266 was already FCC certified, so that's for the Wi-Fi functionality. We also had the no problem. We also had the internal component temperature test. So they need to make sure that of all the components that are in your device, that they don't exceed a certain threshold. They will also do short testing, so they will purposely open up your device and create a short and see if your device catches fire, which I think is really fun. And speaking of fire, they also do fire testing with it. And the last thing that you need to think of is product support. So, we're techies, we like to, play with the toys, but when it comes to it, your support after market is definitely important. So you want to start looking into things like online forums, live chats, phone support, as well as Zendesk and Raygun, like I mentioned before, is something that will give us that crash and exception reporting that your users may or may not report.
So we entered into this thinking about the things that we knew would cost us money, but there was a lot of things that were also unexpected too. So we thought, obviously, buying the parts and paying for labor and getting the plastic for the enclosure, those types of things are all things that you can think of that you have to have when you go with when you manufacture a product. The things that really took us by surprise, some of them because we didn't anticipate them, and some of them because we didn't anticipate they would be so expensive, were things like the mechanical engineering design. Just because we have a plastic case doesn't mean that it's a well-crafted plastic case. So that's where the mechanical engineer comes in. And these things are, they're dealing with like hundredths of a millimeter in measurements and accuracy. Also, the iterations. Carey touched on this with certification. As soon as they find a problem with it, they tell you about the problem, and then you have to go back and recreate another PCB with the fix all implemented, and then give it back to the certification house, and then they'll tell you, okay, that passed that problem, here's the next one. So all these iterations cost time and money. The molding for the enclosure, when they make injection molding, there's actually a metal enclosure that the liquid plastic is squirted into, and making that molding ran us about $20,000. So that's something you definitely want to make sure that the mechanical engineer is done with his revisions before you go to market and have the molding created. And that's actually the phase that we're in right now, is our molding is being fabricated because the mechanical engineer finalized his design a couple weeks ago. And the turnaround for the molding is about a month. So here in another couple weeks, we'll actually have real injection molded plastic instead of the 3D printed ones. Certification and tooling and documentation. We have some things patented, and lawyers are very expensive, and also the server and data hosting. These are all things that maybe in hindsight seem obvious, but we certainly didn't anticipate the magnitude of the costs going into the product.
Other hidden costs include actually doing the shopping around. So there's a large variety of different companies out there that provide services for like PCB manufacturing, as well as population. Same thing with UL certification companies. So there's a lot of companies that work closely with UL. So they will actually do pre-tests for you before you actually go for the official test. And in some cases, the partnership is so tight that they can actually perform the official test and just provide the results to UL. And that's where the company that we chose does. I mentioned this before. Make sure that you know about the minimum quantity for ordering. That one will make you take that cost jump up front. So that will definitely increase your startup costs. Design work, so things like logos and packaging. Luckily, we do have, at Falafel, we do have a great designer that we work with, but that's something that you need to make sure that you have on your docket. Marketing is another thing. I don't know if anybody's been out to see some of the commercials or the Facebook ads that we've been putting out, but marketing is the only way to really get your word out in the social environment. And then, of course, we mentioned a couple times that the UL certification iterations, it costs money, but it can really, really slide your time frame. So I think we really lucked out there. So these are our connections. So Upverter was where we did our schematic design. Kiki PCB, which is the service that we used out of China for developing our PCBs. So we have a couple examples sitting up here if you want to come up and look at those. Simpertech is actually one of these very near to one-stop shops. It's a company that's doing our actual population of our PCBs. They're doing the calibration. So for our meter chips, we need to have factory calibration because depending on how things are soldered on the line, that calibration can change from device to device. So we wanted to make it as accurate as possible. And they also are doing the packaging for us. And then SEL is the UL certification company that we're using. So again, they will do pre-testing for us, and they also have the authority to do the actual testing for UL. So those are our connections. So if you have any questions on those, please let us know.
And then finally, while we don't need this to go to market, and we have a plan beyond this, we did decide to launch as a Kickstarter in order to offer a discounted price. And what we're selling on the Kickstarter is below our go-to-market price, in fact. So if you're interested in what we created, there's currently a Kickstarter out there. And I think the current price is $10 per device on this Kickstarter. So it's an interesting approach to the marketing. Before going fully to VC, you can kind of crowdsource some of the initial manufacturing, and that's what we're trying. So that's the end of the talk. We do have a little bit of time, so what I can show. What's your retail price point? 20. That's the target. And the interesting thing, I think we could talk about this. So the interesting thing is that when we start, we gave the slide about the minimal viable product, right? It has to have these minimal features. Well, we actually were a little bit above that in our thinking. We're like, well, it'd be really sweet if we had USB charging in this and stuff like that. So there are some artifacts in this first revision that's going out. Like we have a power supply that supports 5 volts and 3.3. Even though the ESP only needs 3.3, and really the relay is the only 5-volt component that's in it. So there are some residual artifacts like that will be taken out in a later release, so we'll drive our manufacturing costs down, but $20 is about what it's costing us this first small run. So we're selling them at cost. Again, we want to push people to the website. And beyond residential, there's also other things that people pay grade above me are working on, arrangements with companies and enterprises and stuff like that. So residential, we love you guys, and we're able to give this to you as a free, not at cost, but really the goal is beyond residential.
Yeah, so this, we could spend a whole hour on the features that Miwok can do, but we wanted to concentrate on getting you the information that you needed to get your products to market. So if you do have any questions on any of this, feel free to speak up and let us know. Yeah. Is there a reason that you send a data every 5 seconds? Like, did you not have enough memory on the device itself? You can't collect that for a little bit and then send out? Yeah, that is our aggregate. So we are collecting up to 5 seconds and sending it up, and it really comes down to we picked that number because we thought it was a good number for our real-time graphs. So you could see you can see it on the screen right now, slowly moving. But what we also wanted to do is if we tried to make it too chatty, then we're starting to work on that bandwidth cap. So we thought a good number was 5 seconds. If we find out later that maybe we should go to 10, we can do that. It's easy to adjust, but really that was the main reasoning behind it, was just the bandwidth.
Cirrus Logic device samples 4,000 times a second. So it does the integration for us. We just request it to do the integration over 5 seconds. and every 5 seconds we have a pull loop. So that Cirrus Logic chip is our ASIC, right? So our microcontroller every 5 seconds just serially over SPI says, okay, give me the value of this register. And the Cirrus Logic has been calculating the metering values up to that point. So we pull the values out, we send them up to the cloud, and then we basically sleep for the next 5 seconds or something like that. So that's kind of the loop that's happening on the hardware itself. The question also about storage. So storage is also a well, there's a couple thoughts there. So one thought is, what if the device goes offline, or what if the home's Wi-Fi drops because I have Time Warner cable and it goes down all the time. So we have to have a scenario for what do we do in that case? Do we cache it? Do we store it up? So MQTT itself is a queue in itself, so we can keep publishing messages to it and we'll just retain it in memory. But remember, I only have 40K max, and really operating wise, especially when we're dealing with SSL, that 40K drops down to about 10K max, and then there's different consumption guidelines. So you might run a routine, and the routine needs 7K just to load, but then as soon as it loads, it immediately frees up that 7K. So there's memory tricks that we have to play there with the RAM. One thing about this device, though, is if you run out of memory, it panics and it resets, which isn't too painful because it's a quick boot up and we're back to metering again. But still, it's something to keep in mind that the remedy for running out of memory is the device resets itself. So storage-wise, we had thought about, well, if we're offline for a long time and that MQTT queue fills up, we can just log to a file, and then when we come back online, we send it up. One thing that's always in the back of my mind, though, is flash can only be cleared so many times. It's flash memory, so 500,000 times is the average. So if we're writing a file and clearing memory, that could be problemsome. We could ruin somebody's flash chip by writing too many times. Now, the file system that we're using on this device is called SPIFs, and it's intended to kind of scatter the load across the entire address space so that it's not creating a hotspot on the flash. So the problem I just mentioned is kind of mitigated by using SPIFs, but still, I'd rather get rid of the data as soon as I can rather than caching it up. And also, like Carey said, having the data sent up to the cloud every 5 seconds means that the user can see it every 5 seconds without having to try to communicate with the device themselves. So this graph that we're looking at, I have to turn it on and off from here because there's a bug. But this graph that we're looking at,
You didn't turn off this refrigerator.
no. So this graph that we're looking at is a Miwat that's in my in our teammate's house, and he promised me that there's only a lamp plugged into this one. He didn't want me to give me the one with the air conditioning plugged into it. But what we're seeing here is, you saw that I clicked the switch, and that flipped the relay, and you can see where the relay went off on the screen. I just turned it back on there. So that lamp that's in his house right now is pulling about 32, 33 watts. And then we're able to then later figure out where he lives and then figure out the energy rate there and then calculate how much leaving that lamp on has cost him, or forecast out, if he turns the lamp off, or we notice that this lamp is turned on all day long. If he tells us that it's a lamp plugged into this, if you turn it off between these hours, you'll save this much electricity. Do you want us to schedule that for you? So those types of scenarios, or what's another scenario? Another scenario is I have my washing machine plugged into a Miwat. I see that the washing machine has been off now for 10 minutes. Your laundry's probably done. We can send an SMS to your phone telling you that. Or declare that an outlet always has to be on because there's a sump pump plugged into it. And if that sump pump stops phoning home, you can notify the user, hey, there's probably something wrong with the sump pump because the circuit hasn't called home in 10 minutes or 15 minutes. Make sure your basement isn't flooding. Those types of scenarios, having the data in the cloud allows us to enable those types of scenarios.
Yeah, another algorithm that we're using is the phantom energy usage. So even though you have things plugged in and you might not be using them, that we are registering, the the type of trends that it does when it's turned on versus turned off. So we can identify those phantom energy sources, and obviously we can send you recommendations to turn those off when they're not in use. So you have full control. You can see that you have the on-off. Identify is a nice little feature that will actually more blinking lights. So who doesn't like blinking lights?
So if you look up there, that mewatt, the second mewatt, is actually flashing on the screen. The mewatt that's in his office is doing that same flashing right now.
And by the way, all the actual physical appliances, they're all in Texas. So we're turning on and off lamps in Texas, and I was hoping that he didn't give you his refrigerator. I'm like, you didn't turn off his refrigerator, did you? But yeah. So any further questions? So one of the main things is you have to have dedicated hardware people. So one of the things that we thought was, because we had it prototyped early on and what we thought was close to finished, it's really not that case. We've had our hardware guy going nonstop 40 hours, actually more than 40 hours a week, a lot more than 40 hours a week. But you have to dedicate people to just hardware. So there's not really a trade-off to being able to do both unless you really push your timelines back. Yes? So engaging resellers. So we actually have people coming to us at this point. So it's a good place to be. So I think that comes down a lot to the marketing, and we also have, I guess, a heavy hitter on our board that has connections into a lot of venture capitalist firms. But we, right now, are not opening ourselves up to VC just yet. But just the word getting out, we've had multiple companies contacting us. So ranging from corporations to hotel chains, to just individual users that are interested in the product. So it's a little bit, I don't know how to get.
And the question was, at what point do we engage retailers? Did I hear that question right? Yeah. So before it's done is the answer. So we've already engaged some retailers, and that's through the connections that you said on there. And then after we launched the Kickstarter, we had more people approaching us directly outside of the Kickstarter type of thing. So we have plans for large scale, but then that scares the crap out of me because my software is running on more than a room full of devices. The question was, is the value here the platform? We think it is. Yeah, so this first form factor is obviously intended for the residential market. It's intended for one outlet to plug it into the wall. On our roadmap, we have probably a half dozen other form factors, including things like a surge strip or things like in the wall outlet that you would replace your outlet with, either new construction or remodeling, or even things like a light switch. Put just the electrical metering into that light switch, or maybe the relay too, so that when you flip on your bathroom light, you know that all the electricity going through that one switch is this much. So there's a lot of form factors there, but yes, we feel that the platform is the most important part. That's why we're making our hardware more or less commodity. Back there in the back. So the question is, how public or private are we making this? And this will be the last question. Will be available afterwards, by the way. So our goal is that we'll provide some aggregate information through this. So when you assign or when you plug an appliance into a mewatt, for instance, a refrigerator or a TV, we would love for you to tell us the make and model of that so we can compare that to other people using that same make and model. And for like a refrigerator, we can then notify you, hey, you're like 25% more expensive than everybody else using this refrigerator. Maybe it's time for maintenance. So that type of aggregation is what we're looking to, go ahead, is what we're looking to enable. But on a personal level, on an account level, so if you have MeWatts installed and you're sending information up to the cloud, we would love for you to be able to use your own information. Maybe like an IFTTT type of thing, or open up the API so that you can query it yourself. As long as it's not something like the load's going to bring down our servers because you're requesting it too often or something like that, I think we're okay with allowing you to have access to your own data. So that's all of our time. If you'd like to see the device that we made and stuff, I think we'll step out into the hallway and you can talk to us there. But thanks so much for coming and thanks for the questions.